Every modern car has a hidden system that can literally decide between life and death during braking. It's called ABS, or anti-lock braking system. When you slam on the brakes without ABS, the wheels would lock up immediately, stopping their rotation. Your car would then slide uncontrollably over the surface, and you would lose the ability to steer. That's dangerous, especially on wet or icy roads. ABS prevents this from happening. Its main goal is to keep the wheels turning just before they would lock, maintaining both grip and control. Instead of one long skid, ABS rapidly pulses the brake pressure, so the car slows down effectively while still allowing you to steer. How ABS works in simple terms. The system constantly measures the speed of each wheel. When it detects that one wheel is decelerating too quickly, about to lock, the control unit reduces the braking pressure on that wheel. As soon as the wheel begins to spin again, the pressure increases. This cycle repeats 15 to 20 times per second, creating that distinctive pulsing feeling in the brake pedal, a sign that ABS is actively working. The purpose of ABS: prevent wheel lockup, maintain directional control, shorten stopping distance on most surfaces, keep the car steerable, even under full braking. Without ABS, drivers had to manually pump the brake pedal to prevent skidding. Today, the system does this automatically, faster and far more precisely than any human ever could. For ABS to work perfectly, it must know exactly what each wheel is doing at all times. That's achieved through three key components: wheel speed sensors, the electronic control unit, ECU, and the hydraulic control module. Together, they form the brain and muscles of the entire system. Wheel speed sensors. The eyes of ABS. Each wheel has its own speed sensor that constantly monitors its rotation. Most modern cars use inductive or Hall effect sensors, mounted near a toothed ring, also known as a tone ring, fixed to the hub of the wheel. As the teeth pass the sensor, they create a series of tiny electrical pulses. The frequency of those pulses tells the ECU how fast the wheel is spinning. If one wheel suddenly starts to decelerate faster than the others, the system recognizes that it's about to lock, and that's the trigger for ABS intervention. The ABS control unit, ECU, the brain. The ECU receives signals from all four sensors and continuously compares wheel speeds. When it notices that one wheel slows too rapidly, it sends a precise signal to the hydraulic module, telling it to reduce the brake pressure on that specific wheel. Once the wheel begins to rotate again, the ECU commands the module to restore pressure and resume full braking. All of this happens in milliseconds. The ECU performs hundreds of calculations per second, constantly maintaining an optimal slip ratio, usually between 10–30%. That's the sweet spot where maximum braking force and steering control coexist. The hydraulic control module. The muscle. The hydraulic unit sits between the master cylinder and the individual brake lines leading to each wheel. It contains a set of electromagnetic valves and a pump that precisely regulate brake fluid pressure. Each wheel circuit has its own valve that can increase pressure, braking harder, hold pressure, maintain braking, decrease pressure, release the wheel. When ABS activates, these valves open and close up to 20 times per second, creating the well-known pulsing effect on the brake pedal. That vibration isn't a problem. It's the system working exactly as it should. How it all works together: the sensors detect that one wheel begins to lock. The ECU processes the data and commands a pressure reduction. The hydraulic valves release pressure for that wheel. Once it spins freely again, the pressure is restored. The cycle repeats until the car stops safely. All of this happens faster than any human could ever react. Additional features of modern ABS. Today's ABS systems don't work alone. They're integrated with other advanced safety systems such as EBD, electronic brake force distribution. Balances braking power between the front and rear axles, TCS, traction control system, prevents wheel spin during acceleration, ESP, electronic stability program, stabilizes the car when cornering or sliding. ABS is no longer just a braking system, it's the foundation of modern automotive safety technology. When you hit the brakes hard, your car becomes a real-world physics experiment. In just a fraction of a second, forces, sensors, and hydraulics all react simultaneously. The ABS system engages instantly, far faster than any human reflex. To understand how it truly works, let's explore what happens during braking, how it affects stopping distance and control, and clear up a few common myths about braking without ABS. The classic skid: imagine you're driving on a wet road and you suddenly slam the brake pedal. Without ABS, your wheels lock up and stop spinning. Your tires lose grip and start sliding across the surface. In that moment, you've lost all control over the car's direction. No matter how hard you turn the steering wheel, the car will continue straight ahead. Why? Because a locked wheel creates kinetic friction, which is weaker than the static friction of a rolling tire. That means your car actually brakes less efficiently when the wheels aren't rotating. In short, locked wheels equal loss of control and longer stopping distance. Braking with ABS. Controlled slip-abs is based on a simple physics principle. The maximum braking force is achieved when a tire is just on the verge of locking up, slipping slightly, but still rolling. This is called optimal slip, around 10 to 30%. ABS automatically keeps each wheel within that range. It continuously monitors rotation speed and adjusts brake pressure in milliseconds. If a wheel slows too much, pressure drops. If it spins too freely, pressure rises again. The result is a perfect balance between traction and braking power. That's why when ABS activates, you feel the brake pedal vibrating under your foot. It's the system rapidly pulsing hydraulic pressure to keep the car stable. You don't need to do anything. Just press firmly and keep steering. ABS handles the rest with superhuman speed. Real dash. World results. Control and safety on dry asphalt. ABS might not always shorten stopping distance, but it keeps the car steerable and stable, allowing you to avoid obstacles even under maximum braking. On wet, icy, or slippery roads, the difference is dramatic. A car with ABS remains stable and responsive. A car without ABS can easily spin or slide out of control. Tests from DECRA, Euro NCAP, and NHTSA show that ABS can reduce stopping distance by 10 to 30% and lower the risk of skidding or loss of control by up to 80%. Common myths about ABS. ABS always shortens stopping distance. Not always. On loose gravel, snow, or sand, locked wheels can dig in, sometimes stopping faster. But with zero steering control, ABS keeps you safe because you can brake and steer at the same time. The pedal vibration means something's wrong. Nope. That pulsing is a good sign. It means the system is working perfectly, regulating pressure several times per second. A skilled driver can brake better than ABS. Impossible in real conditions. No human can modulate pressure 20 times per second across 4 wheels. ABS works the same in every car. Different cars have different algorithms. Sporty vehicles allow a bit more slip, while SUVs or hybrids activate earlier. How to brake properly with ABS: press the brake pedal firmly and don't release it. Don't pump. The system does it automatically. Keep steering. The wheels are still turning so you can maneuver. Don't panic when you feel vibration. It's just the system doing its job. ABS is a perfect example of human engineering mastering physics. It lets drivers stop safely while keeping full control. That's why, since the early 2000s, ABS has become mandatory in all new vehicles in the EU and US. Today, we take ABS for granted. But behind this system lies a long history of experimentation, engineering breakthroughs, and innovations that transformed vehicle safety forever. From early mechanical prototypes to advanced computer-controlled systems in electric cars, ABS has evolved into the core of modern automotive stability technology. The origins of ABS. the idea of preventing wheel lockup dates back to the 1930s. In 1958, the British company Dunlop introduced the first mechanical anti-skid system for aircraft, installed on the Avro Vulcan bomber. Automakers began experimenting with ABS in the 1960s, but those systems were slow, unreliable, and expensive. The real breakthrough came in 1978, when Bosch and Mercedes-Benz launched the world's first electronic ABS in the Mercedes S-Class, W116. For the first time in history, a computer could actively control braking pressure in real time. It was a revolution, and soon, every major car manufacturer followed. By the 1990s, ABS became a standard feature in most passenger cars, and since 2004, it has been mandatory in all new vehicles sold in the European Union. Modern generations of modern ABS systems are far faster and more sophisticated than their early versions. While early systems made 5 to 10 pressure adjustments per second, today's microprocessor-based systems perform up to 50 corrections per second. Advanced sensors now measure not only wheel speed, but also steering angle, lateral acceleration, and brake pressure. This data allows the system to adapt in real time, adjusting for surface, load, and driving style. ABS has evolved from a single safety feature into a network of interconnected systems, all working together to keep vehicles stable and drivers safe. How ABS connects with other systems. EBD, electronic brake force distribution, automatically distributes braking power between the front and rear wheels, depending on vehicle load and weight transfer during braking. TCS, traction control system, uses ABS sensors to prevent wheel spin when accelerating. If one wheel loses traction, TCS reduces engine torque or applies the brakes to that wheel. ESP, electronic stability program, the evolution of ABS and TCS. It monitors steering angle, yaw rate, and vehicle trajectory, and if the car starts to skid, it applies selective braking to individual wheels to bring the car back on course. Together, these systems form the foundation of active safety technology, helping prevent accidents before they happen. ABS in the era of electric and hybrid. Cars' electric and hybrid vehicles bring new challenges. They combine regenerative braking, where the electric motor acts as a generator, with traditional hydraulic braking. Modern ABS must coordinate both, ensuring seamless braking, safety, and maximum energy recovery. Manufacturers like Bosch, Continental, and ZF are developing integrated brake control (IBC) systems that combine ABS, ESP, and regeneration into one unit. The result: faster response. Times reduced wear on brake components, greater energy efficiency. It's ABS reimagined for the future of electric mobility. Conclusion: why ABS changed the world, prevents wheel lock and uncontrolled skidding, keeps the car stable during emergency braking, works hand in hand with other systems for total safety, saves countless lives every year. From early mechanical devices to intelligent sensor-driven technology, ABS represents one of humanity's greatest engineering achievements in mobility. It's not just about stopping faster, it's about stopping safely, with control and precision. The next time you feel your brake pedal pulse, remember, that's technology working faster than human reflexes to keep you alive.